Hello, everyone. In this video, we'll start talking about section 6.3, which is dedicated to orthogonal projection. In particular, the topic of this video would be talking about orthogonal subspaces. What we mean by that is given by the following definition. Suppose you get some vectors inside Rn, and then we can define, given that set of vectors, the orthogonal complement of it as the set of all the vectors in Rn that are orthogonal to the given vectors. So the orthogonal complement written in mathematics language is the following set. It's the set of all the vectors in Rn. We'll denote it by S with a little perpendicular sign up here. It contains all the vectors V in Rn such that V is orthogonal to U for all vectors U inside our given set S. In other words, what we're saying here is that for every set, for every element in S, all of the elements in the orthogonal satisfy that their dot product must be equal to 0. Let's have a look at some examples. Here, I let S be the span of my vector 1, 1, and I want to compute the S perpendicular. Well, let's see. Any vector inside S is a scalar multiple of 1, 1 by definition of span. So if I want a vector U that is in S perp, in the orthogonal of S, what I need to make sure of is that I get a 0 when I compute this dot product. In other words, when I multiply the vector CC times U1, U2, I must be getting a 0. This dot product here is CU1 plus CU2. In other words, this is telling me that this must be true for all C in R. In particular, it's true for C equals 1. So for example, in particular, we must have that U1 plus U2 is equal to 0. And we can rewrite this as U1 minus U2. In conclusion, what we can get out of this is that the set S perp is the set of all vectors U such that U1 is equal to minus U2, which is nothing but the span of 1 minus 1. Yeah. It's drawn in this picture here. You see that the set S is the line that is spanned by the vector 1, 1. And then the perpendicular line is exactly the orthogonal complement to S, and it is the span of the vector 1 minus 1. That's this vector down here. Okay. Another example, again in R2, so that we can actually get a good grasp of how these examples look like. Suppose that S is my x-axis, so I can write that as the span of the vector 1, 0, which is the first standard vector, the horizontal one. Then it shouldn't be too hard to conclude that the orthogonal complement to that space is nothing but the y-axis as perp from this picture. But let's try to actually check it by saying that every element of S perp must be orthogonal to any element in S. So having that dot product equal to 0 is the same as saying that U belongs to S perp. Now this dot product here is nothing but X times U1, and this must be true for all X in R. So the only way that this holds is that U1 is equal to 0. In other words, U looks like 0, U2 belongs to the y-axis. So you see that the orthogonality is behaved in the correct way here. in the way that we expected from the picture. Let's have a look at some other examples. The orthogonal complement of the zero vector is the whole space Rn, because every vector in Rn is perpendicular to zero, because the dot product will always give you a zero. Conversely, the orthogonal complement of the whole space Rn is the zero vector. To think about this, what you want to understand is that a vector in the orthogonal complement of Rn is actually perpendicular to every vector in Rn. And the only vector that does that, the only vector that is perpendicular to all other vectors, is the zero vector. Because you can think of it like this. If there was a non-zero vector, so if V in Rn is non-zero, then V dot V, which is its length squared, is different from zero. It has some length. And so V does not belong to Rn perp because it is not perpendicular to all the vectors in Rn. In particular, it's not perpendicular to itself. In other words, the only vector that can be perpendicular to all the vectors is the 0, 1. Let's have a look at somewhat a juicier example. It's a little bit more interesting because it's less special as a case. Suppose I give you the space W, which is given by U1, U2, and U3 vectors such that U1 is equal to U2. And we want to compute W perp. I drew a picture here, and well, let's make sure that the picture makes sense. A vector in UW has U1 and U2 the same, so I can write it as is written here, U1, U1 again, and U3. In other words, I can write it as a linear combination of 1, 1, 0 plus 0, 0, 1. In other words, W is the span of these two vectors. 1, 1, 0, and 0, 0, 1 are a basis for W, and those are the vectors that I drew here in orange to span this plane in R3. Now, the picture here tells us that W perp is going to be a line because the only set of orthogonal vectors to a plane must be exactly this line. If you try, I encourage you to try to think about this picture a little bit and convince yourself that nothing but that line can be perpendicular to that plane. So how do we determine what that line is? Well, for a vector V to be perpendicular to all the vectors in W, it's enough that it is perpendicular to a basis of W, these two vectors here. The vector 1, 1, 0 and 0, 0, 1. So now let's write down what that entails. Having 0 equal to V dot 1, 1, 0 means that V1 plus V2 must be 0. And likewise, we have that 0, 0, 1, V3 must be 0. That's the product we get there. So the vectors in W perp look exactly like this. V1, from here, we get that V1 is equal to minus V2, or rather, let me write V2 is equal to minus V1. It's the same, but it fits the writing that I have here. We have V1 minus V1, and then V3 must be 0. In other words, W perp is the span of 1 minus 1, 0, which, if you draw it in this picture, it's exactly this vector. Okay, let's focus on another substantial example. I give you a matrix A, and we want to find the orthogonal to the row space of A. So the way we want to do that is by, well, first of all, computing a basis of the row space of A, and then computing the conditions for a vector to be orthogonal to that basis. So the way we find a basis for the row space of A is the usual. We compute the reduced row echelon form of A. You can check the details here, but what you get is this matrix over here for a reduced row echelon form. And then from the reduced row echelon form, we can just read out a basis for the row space of A, which is given by the non-zero rows, 1, 0, 0, 1, 0, 2, 5, minus 2. And those are the ones that are collected here on the right. Okay, so what does it mean for a vector to be in the perpendicular in the orthogonal complement to row of A? This means that V must dot with 0 against this vector. But when I multiply and I compute this dot product, I get V1 plus V4. Those are the two entries of V that are getting selected there. Maybe allow me to write it like this. I'll write V as V1, V2, V3, and V4. The other condition is that V1, V2, V3, and V4, the condition is that this is equal to 0. That's the perpendicularity condition. The other is that 0 is what you get when you multiply this by 0, 2, 5, and minus 2. In other words, that reads 2v2 plus 5v3 minus 2v4. Now, let's take a look at these conditions here. I claim that any vector that satisfies these two, 1 and 2, is a solution to A dot V equals 0. Let's have a look at why. If I multiply this vector V1 through V4 times the matrix A, I get exactly zeros because the solutions to the AV equals 0 are given by the row reduced echelon form of the augmented matrix. And you see that the rows there, when you translate them to equations, become exactly the same equations. You get V1 plus V4 is equal to 0 here, and that's the first solution. And the second is exactly 2v2 plus 5v3 minus 2v4 equals 0. So what we just showed here is the following implication. If you have a vector inside the orthogonal of the row space of A, then that same vector is inside the null space of the matrix A. And conversely, if a vector is a solution to the homogeneous linear system, then it will be orthogonal to the rows of A. Wrapping up what we proved, it's the following fact. The orthogonal to the row space of A is indeed the null space of the matrix A. Let me conclude this video with a few properties of orthogonal subspaces. I'll just comment on them very briefly, and some of them will show up again in a workshop soon. Let's have a look at them. Well, first of all, this first one is maybe the most crucial one. The orthogonal complement of any subset, any set of vectors, is always going to be a subspace. Orthogonality is a property that behaves well with rescaling and with adding orthogonal vectors together, which are the two key features of a subspace. So every orthogonal complement is a subspace. This second property is something that we've actually already used. If I want to look at the orthogonal complement of the span of a set, I can just compute the orthogonal complement to that set. So when we wrote W is the span of maybe a couple vectors, all we did to compute W perp was to compute the perp to those two vectors. And this property tells us that we can, in fact, do that. the other two properties? Well, the third one is something of which we got a glimpse. The dimension of a subspace and its orthogonal complement must be the dimension of the whole space. I remind you, when we saw the example that involved a plane, that the orthogonal complement to that plane we computed was a line. And in fact, we have dimension 2 here and dimension 1 here. If you add them together, you get 3, which is the dimension of the ambient space, R3. It's an example from the ones above. Lastly, the last property is the one that we commented on above. The perpendicular space to the row space of A is the null space of A. But remember that this teaches us a little bit more, because the column space of A is the row space of A transpose. So if I take the orthogonal complement of the column of A, that's the same as taking the orthogonal complement of the row space of A transpose, which is the null space of A transpose. So this we showed above, and this is a simple consequence of it by remembering that the column space of A is equal to the row space of A transpose, and conversely. Okay. This is the end of the video, and I'll see you in the next one.